Hashing is another form of cryptography. It is unique in the fact that the output of a hashing function is never meant to be decryptable. We refer to hashing as a one-way function. So let's look at this in a little more detail here. Let's get some definitions. Hashing, also called a one-way hash, creates a ciphertext, and we usually refer to this as a hash from some plain text. And again, it doesn't have to be text. It could be any sort of digital information. Hash algorithms are used to verify the accuracy of a value without transmitting the value itself, and therefore subjecting it to attacks, and we're going to look at some examples of this. The book mentions that a practical use of a hash algorithm is with ATM cards. The big thing here is you don't want to transmit the user's PIN number across the network back to the the mother bank, the mother computer at the central processing center. So you use a hash of the PIN. And this is also done with passwords. We'll look at this and I'll mention it later. So let's look at a basic diagram of hashing. So we're going to start out with the something to be hashed, and in this case it's going to be something digital. Could be a document, could be a password, could be a PIN number. This is going to be fed into the hashing algorithm. An algorithm is a procedure. It's usually, or it's often mathematical. So we feed our input into the algorithm, and what we get out is a hash. So this is the output of the hashing algorithm. Now, if you take a hash and feed it into a hashing algorithm, you're not going to get back to the original thing. What you get is a hash of a hash. The thing to remember is you don't get the original input. So we say hashing, the process of hashing or hashing algorithms are one-way functions, and this means it's easy to perform the algorithm or execute the algorithm in one direction, but it is really, really hard to go back the other way. And actually, if you have the right algorithm, it's could be for all intents and purposes impossible to go back in any reasonable time frame. Some other uses of hashes: digital signatures, which we're going to talk about in more detail. Password hashes. You never want to transmit a password in clear text across the network. You never want to store user passwords in clear text or plain text form. What you store is password hashes. And when you log on, basically what it's done is the hash of your password is compared to the stored hash of your password, and if they match, we assume that you did know the original password. We can also have hashes of files. This is used to verify that the file has not been modified or hacked. If you're interested in more of this, look at there's an application called Tripwire. I think there may even be a free for personal use version of this. I'm pretty sure, I know there is for Unix/Linux. There may be one in Windows. I know there's a Windows version you can pay a nominal amount of money for. But anyway, what Tripwire does in similar applications is it calculates the hashes of all the files on your system and stores them, and it periodically goes back and checks the files, and if the hashes don't compare, it tells you that something's been changed. So we also have hashes of files, or even entire drives when we're copying. If we're doing forensics work, we use hashes to verify that a copy or a file, or files, or even the whole drive is identical to the original. This is very important in forensics. So in forensics we talk a lot about hashes. Here's a very simple example of hashing. In this case, we take a numeric input. We simply multiply it by something. Our algorithm here is the input value times the multiplier. The result is some large number. Now, even from this simple example, you should be able to note here that it's going to be difficult to take this number and get back to this original value. Not to say that it wouldn't be impossible in this case, because this is a very simple example. Real cryptographic algorithms are much more complicated than this, but this just gives you some idea of the process. Let's look at some characteristics of a good hashing algorithm. One of the characteristics is the two different inputs should never produce the same output. Now, when this happens, this is called a collision. It's actually impossible to guarantee that there will never be a collision. And the reason for this is there are an infinite number of possible inputs, but there's only a fixed number of possible output hashes, and this fixed number is based on the number of bits in the hash itself. But a properly designed algorithm is going to make this highly unlikely that you'll ever encounter a collision. So theoretically it's possible to have collisions, but practically speaking, we want an algorithm that is going to make it very, very, very unlikely that we'll ever see a collision. Another characteristic of a good hashing algorithm is that changing a single byte in the input should produce an entirely different output, such that we couldn't predict, or we couldn't see any pattern in the two different hashes. It should also be impossible to create a message that has a desired hash output. If this were true, you could manipulate an input to create a particular output, and that's not going to be a good algorithm. More characteristics. It should be impossible to take a hash and use it to generate the original input. We talked about this earlier. Hashing should be a one-way function. The hashing algorithm itself does not need to be kept secret, and the good ones aren't. They're all out there in the public domain. The algorithm should produce, or will produce, a fixed size output for any sized input. What we mean here is a single byte file should produce the same size, hash, size in bytes, as an entire hard disk. Now the book gives an example here of hashing as a way to thwart a man-in-the-middle attack. Now, a man-in-the-middle attack is any sort of attack where some person, computer, or whatever is basically placed in the middle of two other computers or people, whatever, that are communicating. It's pretty much what it sounds like, a man in the middle. So let's look how hashing would be, or could be used to thwart a man-in-the-middle attack. We've got our original plaintext message here. You are hired. We run it through our hashing algorithm. We generate a hash. We send this along with the message. The man-in-the-middle attack here is we're actually going to modify the message. We're going to change the H to an F. And this is the recipient. That's where this happens at. This is all on the sender's end. At the recipient end, we're going to run the same. We're going to run the message itself through our hash algorithm, and we're going to same hash algorithm. We're going to generate the hash. In this case, these two hashes don't match, and since they don't match, we know the message has been modified. And this is an integrity issue. I've talked about this before. The book talks about this. The integrity of the message has been compromised. It's been changed. Now, you may be looking at this, and I hope you're looking at this, and you're saying, well, why didn't the man in the middle change the hash that's being transmitted? Well, there's a way we can ensure that this can't be done. We'll talk about this later when we talk about digital signatures. So remember your question when we get to the part on digital signatures, and you'll see how we can could use cryptography to make sure that the man in the middle can't change the hash, and therefore hide the fact that the integrity of the message has been compromised. So keep that in mind. I'll try to remember it too. Let's briefly go over some couple of the popular hashing functions. There's a kind of a family of functions called message digests, abbreviated MD. I'm not going to go over every one of these. The big thing about message digest is it produces a hash that's 128 bits long. That's MD2, that's MD4. Now, there was some little issue with MD4, so MD5 was a revision of this. This is also 128 bits. MD5 is used extensively. If you want to play around with this, there's an application called MD5 Summer that's free utility that help if I could spell, a free utility that that generates MD5 hashes, and you might want to download this and actually play with it. If you if you download a lot of things from the internet, you may have already run across places where, along with the files to be downloaded or available for download, there are also links there beside of it that says MD5 or SHA1, which we're going to talk about in a moment. What's going on here is the people running the website have provided the hashes of the files that you can download. So you can download the files and check the hash and make sure that you can verify that it matches the hashes that were on the website. You can therefore verify that there was no change in the download. And this is an interesting function. You may have seen these things marked MD5 and SHA1 and wonder what they were. Well, they're hashes. So that's a message digest. Briefly again, here we're going to just mention the SHA algorithm, the SHA. That's the way it's usually pronounced. If you're interested in taking the Security Plus exam, this is the kind of thing you need to know about these algorithms. Is the bit length. SHA1 is 160 bits instead of 128. This makes it more resistant to attacks than 128. And we're not really worried about how SHA works. There's some information in the book you can look at if you want to. A lot of heavy-duty mathematics, and for our purposes, we really don't need to know that much about the mathematics. We just need to know how to use these tools. So that's a somewhat more in-depth introduction to hashing. Now we will revisit this concept when we talk more about digital signatures. So you want to keep that in mind.